This is the third video of this chapter, in which we will look at different regulators. In the following, we will introduce series controllers, also known as series compensators, which are connected in series to our plant in this configuration. In the example with the negative feedback, the logic of the regulator was a simple rule. Our first structure also works in a similar way. One of the simplest regulators is the bang-bang controller, also known as on-off regulator, which has two states and can switch between them. At first glance, this technique may seem a bit primitive, but for many applications there is no need to overcomplicate things. For example, this control is also the basis of the thermostat, where to keep the water at a given temperature, the heating either switches on or switches off when the ideal value is reached. To avoid continuous on-off switching, a hysteresis is used. Let's say you want to keep the water temperature at 70 degrees Celsius, so the lower comparator level is set to 60 degrees Celsius and the upper is set to 80 degrees Celsius. This way, there will be less switching on and off, as state changes only occur at these two values.
The bang-bang controller is activated when one of the comparing levels is reached by the controlled signal. Continuing with the previous thermostat example, if the water drops below 60 degrees Celsius or rises above 80. This means the temperature is free to move, so to speak, within the range of 60 to 80 degrees, which our controller does not care about, while we want the water to be at 70 degrees. What if, knowing the temperature of the water, if it went above 70 degrees, the higher the temperature, the more cooling we would apply, and if it went below 70 degrees, the colder it is, the more heating we would apply. In this case, we use a PID controller. The proportional term calculates its output by multiplying the incoming error term by a constant Kp. The advantage is that it is very simple. The disadvantage is that when using a proportional controller, it is not guaranteed that the controlled quantity is exactly the same as the set point. This is called residual error.
To understand this, imagine a system with output y equals 0.5 times e, where e is the error signal and y is the output signal. Let the output of the system at the initial instant be, for example, 20, denoted by y1. We want the output to be 30, so we set the reference signal to 30. Then, the next instantaneous value of y is obtained as follows. The error signal e is the difference between the reference signal and the output value, which is now 10. Y equals 0.5 times e, so y2 is 5. From this, we get the output as the sum of the two values, which is 25. At the next point, we see that the output will now increase less because of the smaller error signal. It's easy to see that no matter how many times this process is repeated, it will never reach the desired value, so we'll always have a residual error.
Now let's take a look at the block diagram of the PID regulator. The formula of the actuating signal generated by the controller as a function of time, where Kp is the gain of the proportional term and E is the error signal. The next figure shows that with the PID controller, the controlled characteristic moves within a much smaller range, bringing us closer to the desired value of 70 degrees Celsius.
However, we could not get the output to be always the expected value with any of the regulators. The PI controller can eliminate the residual error. Let's see what that looks like. To avoid this error, we will build an integrator into our controller in addition to the proportional term, which will be responsible for eliminating the residual error. The word integrator means a summation. The function of the integrator is to add the current error to the previous error amount at each time step and multiply it by a constant ki. This is effectively information about the past. The number of time steps the error signal is not zero. The number of time steps the controller increases or decreases the value of its output, thereby eliminating the residual error. The output of the controller is the sum of the proportional part and the integrator. This gives the formula of the actuating signal generated by the controller, where Kp is the proportional gain, Et is unchanged the error signal, and Ki is the integrator gain. Although the residual error is eliminated, the integrator term will cause the system to settle more slowly to the final value, its overshoot will increase, and its stability will deteriorate.
If we want to improve the response time of the controller, we need to implement a differential component in our controller. The PID controller is appropriate for this application, so we will proceed with it. In this case, the controller consists of two parts, a proportional and a differential part. The differential component in this case shows the change of the current error. It can be understood as an error estimation one step ahead. The differential is the difference between the previous error and the current error divided by the sampling time and multiplied by a constant kd. The output of the controller is the sum of the proportional and differential terms. Based on these, the formula of the actuating signal generated by the controller, where Kp is still the proportional gain, Et is the error signal, and Kd is the differential gain.
The ideal differentiating term cannot be implemented in reality. Instead, an approximate differentiating term is used. In the present case, we have improved the transient decay time, but in the absence of an integrating term, the residual error reappears. If we combine the PI and PD controllers, we would maintain the benefit of the differential gain, while the integrating term would eliminate the residual error. In the 20th century, Nicholas Minorski came to a similar conclusion when he observed a ship's helmsman. He steered the boat by not only correcting the current course error, but also by taking into account the behavior of the sea up to that point and correcting for permanent disturbances such as strong winds. These three factors perfectly represent the proportional, differentiating, and integrating members. This theory was elaborated by Minorski in a control theory in 1922 and later became the basis for the PID controller. Let's look at its control chain. Considering the foregoing, this controller summarizes all the types of controllers used so far. It contains the pre-proportional, the I-integrating, and the D-differentiating component, while the output of the regulator is the sum of the individual components. The formula of the actuating signal generated by the controller is also the sum of the three terms, where Et is the error signal and K is the gain of each term. In practice, the challenge is not to implement such a controller, but to set it up so that it is working properly.
Before moving on to the topic of adjustment, I'd like to talk about the applications of PID. The PID controller is widely used in industrial control engineering. It is used to control temperature, flow, speed, pressure, and many more. It is used for heat treatment of metals because the sequences require precise control to achieve the desired metallurgical properties.
PID control is also an option for evaporation of solvents, where accurate temperature control is required. Too high a temperature can damage the substrate, while too low a temperature can damage the product and result in a poor appearance.
In rubber curing, precise temperature control helps vulcanization without adversely affecting the properties of the material.
Commercial ovens must follow a strict heating and cooling sequence to ensure that the necessary reactions take place, so there is no tolerance for errors in the P, PI, or even PD controllers.
It may be helpful to recall the advantages and disadvantages of each type of regulator now. We have prepared a table to help you decide which one to choose later. The bang-bang regulator is not included in the table because in almost all cases the more accurate P regulator can be used. It has the advantage of simplicity, which is why overshooting and residual error can occur with its use. There is no residual error with the PI regulator, but in return it is slower and more unstable, and the transient degrades with higher overshoot. The PD regulator, on the other hand, is fast and gives a nice transient, but the residual error returns. PID has the advantages of PI and PD, but is more complex and more expensive to implement.
Now, let's compare the regulators according to their responses to the step function excitation. It's obvious that the PID controller is the best out of the listed controllers. Only the PD is faster at reaching a final value, but this is an incorrect value. Its overshoot is minimal, even compared to the PI. However, choosing the PID may not always be the best choice if the task can be solved with a much simpler and cheaper controller. Stay tuned for the final video of Chapter 18, where we'll look at the setup methods and review 2 real-life examples. Bye-bye.
Bye.